Hello friends, this is my fifth lecture on Cauchy type integral equations. Here we will first define Cauchy principal value for contour integrals. So let C be a closed or open regular curve, and we enclose the point z0 by a small circle of radius epsilon. So let us say we have a circle curve like this, where z0 is a point on this curve. We enclose it by a small circle of radius epsilon. So then let C epsilon denote the part of the curve outside this circle. If the complex valued function fz is integrable along C epsilon, however small epsilon we take, then the limit epsilon tends to 0, integral over C epsilon fz dz, if it exists, is called the Cauchy principal value, and as we had defined denoted earlier, P integral C fz dz denotes the principal value of this Cauchy integral, or we also denote it by integral over C star fz dz. We will study the contour integrals of the Cauchy type. We have earlier considered Cauchy type integral equations on a real line. Now we are going to define study Cauchy integral equations in a complex plane. So let us look at this Cauchy type contour integral of the Cauchy type, integral over C fz dz over z minus z0. If fz satisfies the Holder condition, mod of fz1 minus fz2 less than k times mod of z1 minus z2 to the power alpha, where z1 z2 are any pair of points on the curve C, k and alpha are constants such that 0 less than alpha less than or equal to 1, then f1z defined by integral over C fz dz over z minus z0, okay, is also Holder continuous, which possesses the same properties as possessed by the corresponding real functions. Now here there is a very important formula which we know by the name Poincare-Bertrand transformation formula. We will not prove this, we will simply use this formula. So let by t be a Holder continuous function and let C be a closed contour. Then integral, then 1 over 2 pi I whole square, the principal value star means, again let me remind you that it is the principal value of the integral over C dw over w minus t, integral over C star yz over z minus w dz is equal to 1 by 4 by t. So this formula plays a crucial role in finding the solution of the Cauchy type integral equations in a complex plane. Now let us look at the Cauchy type integral equations when there is closed contour C. So we will consider the case of those Cauchy type singular integral equations where we are given a closed contour C. So we are going to solve the integral equation given by a by t equal to ft minus b over pi I, principal value of the integral over C by z over z minus t dz, where a and b are known complex constants, by z is a Holder continuous function and C is a regular closed contour. So this called as Cauchy integral equation of the second kind. Later on we shall see that as a particular case we shall also be able to determine the solution for the Cauchy integral equation of the first kind. So to solve this equation we introduce an operator. Let us define the operator as Ly equal to a by t plus b over pi I integral over C star by z over z minus t dz. Then so if we define Ly equal to a by t plus b upon pi I integral over C star by z over z minus t dz, then the given equation 2 can be written as, then 2 can be written as a by t plus b upon pi I integral over C star by z over z minus t dz equal to ft are Ly, the left hand side is Ly equal to Ft. So by defining the operator L as Ly equal to Ayt plus b upon pi I integral over C by z over z minus t dz, the equation 2 may be rewritten as Ly equal to Ft by using the definition of the operator L. Now let us define an adjoint operator. So the adjoint operator we define as we define it mg equal to Agt minus b over pi I integral over C w minus t. So from 4 what do we notice? See, from 4 we have Ly equal to Ft, and therefore now let us recall this equation. This is equation number 4. So from 4 Ly equal to Ft, we then have m of Ly. M of Ly is equal to F, so we have Mf. So applying equation 4 or using equation 4 and the definition of the adjoint operator mg equal to Agt minus b over pi I integral over C dw over w minus t dw, we can write m of Ly equal to Mf as Ly is F. Now, so let us now substitute the value of Ly here. So Ly is equal to Ayt plus b over pi I integral over C by z over z minus t dz. So when we substitute the value of Ly here, we get m of a by t plus b over pi I integral over C star by z over z minus t dz equal to Mf. Now let us say that a by t plus b over pi I integral over C by z over z minus t dz, we denote it by let us denote it by a by t plus b over pi I integral over C by z over z minus t dz equal to gt, then we have gw equal to a by w plus b over pi I integral over C by z over z minus dw. So we will get this as mg equal to Mf. We are writing a by t plus b over pi I integral over C by z over z minus t dz. This is as gt, this as a function gt, and then what we have is this gt can be by changing t to w, we can write gw equal to a by w plus b over pi I integral over C by z over z minus dw z minus w dz, and so mg becomes Mf. So this is this gives you mg equal to Mf, and R. Now mg is how much? By definition of mg we write mg equal to Agt minus b upon pi I integral over C dw divided by w minus t. This is mg, and Mf is equal to Aft minus b upon pi I integral over C w minus t by using the definition of the operator. So now let us replace the value of gt here. In place of gt we write a by t plus b over gt is equal to we are writing gt equal to a by t plus b over pi I integral over c by z over z minus t dz. So in a times a by t plus b over pi I integral over c g in place of gt, okay, in place of gt we are putting this. So a by t plus b over pi I integral over c by z over z minus t dz minus b over pi I integral over c 1 over w minus t, then gw is a by w plus b over pi I integral over c by z over z minus w dz dw, and this is equal to right side, that is a of t minus b over pi I integral over c f w over w minus t dw. Now when we multiply this, this is a square by t plus ab over pi I integral over c by z over z minus t dz, and here what we will have, if you multiply we will have minus ab upon pi I integral over c 1 over w minus t by w. So this and this integral will cancel. Let us multiply, we get a square by t plus ab over pi I integral over c by z dz over z minus t, and then minus ab over pi I integral over c 1 over w minus t, and we have by w dw, and then we have minus b square over pi I whole square integral over c 1 over w minus t by z dz divided by z minus w dw equal to a of t minus b upon pi I integral over c f w dw over w minus t. So you can see here ab upon pi I integral over c by z dz over z minus t will cancel with this, because there is only a change of variable. Here we have w, here we have z, so this will cancel with this, and what we will have then, so we will have a square by t plus this term will cancel with this term, and we will have a square by t plus ab upon ab upon pi I integral over c by z dz over z minus t minus ab upon pi I integral over c by w dw over w minus t. Now this term will cancel with this term, and here to for this term we have used the Poincare-Bertrand formula. So let us go back to that formula and see what is that formula. So this formula tells us that it is 1 over 2 pi I whole square. So by this formula we have using Poincare-Bertrand formula, we have, yes, so integral over c star dw over w minus t integral over c star by z dz over z minus w dz equal to 1 by 4 by t. So, we will have a square by t minus b square upon pi I whole square equal to, and then multiplied by 2 pi I whole square divided by 4 by t equal to a of t minus b upon pi I integral over c star this. Now 4 2 square will cancel with this 4 pi I whole square with this pi I whole square, and we will get a square minus b square by t equal to, so, or we get this. Now, if we assume that a square minus b square is not equal to 0. So, if we assume that, so we come here, if we assume that a square minus b square is non-zero, we can write the value of yt from here. So, yt will be equal to a upon a square minus b square into ft minus b upon a square minus b square into pi I integral over c fz over fz dz over z minus t. We can replace w by z. So, this will give us the solution of the Cauchy type integral equation over a closed contour. Now, this, if you substitute this back into the integral equation, it turns out that this by t indeed satisfies the original equation. We can see it, we can see how it satisfies. So, let us go back to the Cauchy type integral equation whose solution we are trying to find. So, this equation is a by t equal to f t minus b upon pi I integral over c star by z over z minus t dz. This is the Cauchy type integral equation of the second kind. We are claiming that this is the solution of this Cauchy type integral equation. So, let us substitute it in this equation and show that it indeed satisfies this equation. So, let us take the right hand side. Right hand side will be equal to f t minus b upon pi I integral over c star, and then let us substitute the value of by z here. So, by z will be equal to a upon a square minus b square fz minus b upon pi I integral over c star fw, we are writing the value of, okay, so fw dw over w minus z. So, let us see what we get here. This is f t minus a b upon a square minus b square into pi I integral over c star f z dz over z minus t. ft minus ab upon a square minus b square into pi I integral over c fz dz over z minus t dz, and here what do we get? Plus b square upon pi I whole square integral over c star dz over z minus t, then integral over c star fw dw divided by w minus z. Now let us see, we use this formula, Poincare-Bertrand formula. So when you use Poincare-Bertrand formula, integral over c dz over z minus t, in place of w we have z, so dz over z minus t, integral over c, in place of w we have now z, so we have here fw over w minus z dw. This will be equal to 1 over 4 and in place of f we have t, so we have 1 by 4 ft. So this will be equal to so b square upon pi I whole square and then we have 2 pi I whole square by 4 and we have ft here. So what we will get then, so 2 square will cancel with 4, pi I whole square will cancel with pi I whole square, and what we get?
Sir, a square minus b square
We are writing, we are putting the value of by t as 1 upon aft upon a upon a square minus b square b upon pi I a square minus b square. So 1 a square minus b square we have missed here. So let us correct it. A square minus b square integral over c star fw dw divided by w minus t. So this a square minus b square is also here. Here also a square minus b square. So now what we get? ft times 1 plus b square upon a square minus b square, this term plus this term minus ab upon a square minus b square pi I integral over c star fz dz over z minus t, or we can say r a by t equal to, now a square minus b square plus b square will be a square, so a square upon a square minus b square, a square minus a square upon a square minus b square ft minus AB upon A square minus B square into pi I. So wait, so right hand side we are writing, sorry, right hand side we are writing, right hand side is equal, so this right hand side is now equal to AB upon A square minus B square pi I integral over C star fz dz divided by z minus t, and this is nothing but this is equal to A into by t. This is equal to, because you multiply by t here is A upon A square minus B square ft minus B upon pi I A square minus B square integral over C f w dw over w minus t. So you multiply that equation by A, you will get this equation. So this is equal to A by t, and so we get the left hand side, which is equal to the left hand side. So this is how we show that the by t equal to A upon A square minus B square ft minus B upon A square minus B square pi I integral over C fz over z minus t dt dz is gives us the solution of the Cauchy integral equation along a closed contour C. Now in particular, if we put A equal to 0, if we put A equal to 0 in equation number 10, if we put A equal to 0 here, what we will get? By t equal to minus by t equal to, putting A equal to 0, the equation 10 gives us by t equal to minus b upon minus b square pi I integral over C fz dz over z minus t, or we can say by t equal to 1 upon b pi I integral over C star fz dz divided by z minus t. The Cauchy integral equation of second kind reduces to on taking A equal to 0, it reduces to ft equal to b upon pi I integral over C by z over z minus t dz. The Cauchy integral equation ft equal to b upon pi I integral over C by z dz over z minus t. Now this is Cauchy integral equation of the first kind. So when you take A equal to 0, the Cauchy integral equation of second kind reduces to the Cauchy integral equation of the first kind, and the solution of this Cauchy integral equation of the first kind is given by t equal to 1 upon b pi I integral over C fz over z minus t dz. Further, if we take b equal to 1, then what will happen? Then we get the Cauchy integral equation as the Cauchy integral equation of the first kind reduces to ft equal to 1 over pi I integral over c by z dz over z minus t, and its solution is given by t equal to 1 upon pi I integral over c star fz dz divided by z minus t. So, when the integration in the Cauchy integral equation of second kind, we take a equal to 0, b equal to 1, we get this Cauchy integral equation, and its solution is given by t equal to 1 over pi I integral over c fz dz over z minus t. Now, you can see these two equations. Here in this Cauchy integral equation, by z is the unknown function, and to determine by z, what we do is we simply replace by z by fz. So, the two equations from this given equation, it is easy to write its solution. The solution is just replace by z by fz. So, by t equal to 1 over pi I integral over c fz dz over z minus c. So, that is why we say that equations 13 and 14 display the reciprocity of these relations. So, with this we will conclude our discussion on Cauchy type singular integral equations. In our next lecture, we will see how to apply the Fourier transform to solve integral equations. We have already seen how to apply Laplace transform to solve integral equations. Now, we will see the integral equations that can be solved by using Fourier transforms. So, with this I would conclude this lecture. Thank you very much for your attention.